Hey, welcome back. So in our last chat, we really dug into the sine function and how it measures a right triangle's height. But that's only half the picture, right? Today, we're going to tackle the other half of the story, the cosine function.
Right, so if you think of sine as the vertical part, the up and down of a triangle, it just makes sense to ask, well, what measures the horizontal part, the side to side? And that's exactly the puzzle we're solving today. It is the other crucial piece you absolutely need to understand how triangles really work.
And yeah, you guessed it, the answer is cosine. At its very core, cosine is the tool we use to measure that horizontal width of a right triangle. And the way we unlock it is with a super simple rule, adjacent over hypotenuse. Okay, here's the formula you're gonna want to remember. The cosine of any angle, we'll call it theta, is the length of the adjacent side divided by the length of the hypotenuse. Now, the magic word here is adjacent. It's the leg of the triangle that is literally touching the angle you're looking at, just not the hypotenuse, of course. And what's so cool about this, just like with sine, is that this ratio is always constant. I mean, it doesn't matter if you have a teeny tiny little triangle or a huge one. If they have the same angle, that ratio of adjacent to hypotenuse is going to be exactly the same. It all just scales up and down perfectly, keeping that ratio totally locked in.
So the theory is all well and good, but let's get our hands dirty and see how this actually works. We're going to walk through 3 examples, starting out easy and then building up, just to make sure this concept really clicks.
All right, first one up. We've got a right triangle here, triangle KLM, and all the side lengths are right there for us. The question is as straightforward as it gets. What is the cosine of angle K? Okay, let's break this down. First step, we figure out our point of view. We're standing at angle K. Second step, we identify the sides we need. The hypotenuse is always the one across from the right angle, so that's KL, which is 17. The adjacent side is the one touching angle K, which is KM, and that has a length of 8. We don't even need to look at the opposite side. Third step, just build the fraction. Adjacent over hypotenuse, that's 8 over 17. And we're done.
Okay, let's turn up the heat just a little bit. For this problem, we're given the hypotenuse, which is 25, and the opposite leg for angle A, which is 24. And they're asking us to find the cosine of A. See the little trap they've set for us here?
So let's take stock. We have the hypotenuse, it's 25. We have the opposite side, it's 24. But hold on a second. To find cosine, what do we need? The adjacent side. The problem didn't give it to us. This is a classic move on tests to see if you're paying attention. So, what do? Are we stuck? Nope, not at all. We just have to pull out another one of our fundamental tools for right triangles. And that tool, of course, is the good old Pythagorean theorem. Since we have a right triangle and we know 2 sides, we can always find the third. We just set it up. A squared plus 24 squared equals 25 squared. Okay, let's do the math. That gives us a squared plus 576 equals 625. We subtract 576 from both sides, a squared equals 49. Take the square root, and boom, our missing adjacent side is 7. And now that we've found that missing piece of the puzzle, the rest is a piece of cake. The cosine of A is just adjacent over hypotenuse, which is 7 over 25. Problem solved. All right, time for the advanced round. We're looking at a special case, a 45, 45, 90 triangle. The cool thing about these is that the 2 legs are always equal. Let's just say they're both 1 unit long. That means the hypotenuse has to be the square root of 2. Our job? Find the exact cosine of a 45-degree angle. Okay, so if you're at either 45-degree angle, the adjacent side is 1 and the hypotenuse is the square root of 2. So that gives us the ratio 1 over the square root of 2. Now here's a little rule in math. We really don't like leaving a square root in the denominator, the bottom of the fraction. So we rationalize it. All that means is we multiply the top and bottom by that square root of 2. This gives us the square root of 2 on top and the square root of 4 on the bottom. And since the square root of 4 is just 2, our nice, clean final answer is the square root of 2 over 2. Now let's talk for a second about how to avoid some really common mistakes. Because sine and cosine are so similar, it is incredibly easy to mix them up, especially when you're rushing through a quiz or a test. Okay, check this out. This is where so many people trip up. Imagine you've got a triangle where the adjacent side is 5, the opposite is 12, and the hypotenuse is 13. When you're under pressure, it is so tempting to just grab the bigger number, 12, and say cosine is 12 over 13. But that's sine. The right way to do it is to just stop, take a breath, and actually find the side that is touching your angle. That's the 5, so the correct cosine is 5/13. So we've done all this math, but you might be thinking, okay, why does any of this actually matter? Where does cosine show up when I'm not in a math class? Well, let's look at a really cool real-world application. You know, in physics, the idea of work is super specific. It's basically force times distance. But there's a huge catch. Only the force that's going in the exact same direction as the object is moving actually counts. So if you're pulling a sled with a rope that's at an angle, some of your effort is actually pulling up, which is totally wasted. And this is where cosine becomes a hero. The cosine function is the tool physicists use to figure this out. It basically tells you exactly what percentage of your total diagonal pulling force, the hypotenuse, is actually translating into useful forward horizontal force, the adjacent side. It's how they calculate the real work being done. So let's wrap all this up with one last thought to chew on. We've pretty much established that cosine gives us the horizontal component. You can think of it as the x-coordinate. And we already know that sine gives us the vertical component, the y-coordinate. So here's the big question. What kind of amazing things happen when you put those two together? What can they tell us? Think about that, because that's exactly where we're heading next.